join me in the second speaker of the day, Graham MAZZEO.
Thank you very much. So, well, thank you for sticking around till the bitter end. And so I want to get to some sort of conclusion, or at least give some sort of sense of how, as I say, it relates to fractional constants. But so what I've been doing the past 3 lectures is, catching you up in the last 70 years. And so now we're in this year. So I want to actually, before I get to that, I want to sort of fill in a few things I didn't get a chance to say yesterday. So a few omissions. So recall that we had this class of 0 differential operators on manifold M. So this was the set of all things in the form J alpha of x and y, x dx, j, x dy to the alpha. And I assume that these AJ alphas are smooth. You can weaken that somewhat, and this works equally well with systems, so the AJ alphas could be matrices. Okay. So we defined the notion of ellipticity using this symbol, 0 sigma m of L, and this was the sum j plus mod alpha equals m, j alpha of x, y, c to the j, beta to the alpha. So the claim was that this was a natural object, that this is a well-defined object, but on some other bundle. So this is a smooth function on something called the 0 cotangent bundle, which I think defined for you, and it's polynomial in fibers. Okay, so ellipticity means that this is an invertible symbol. Okay, so the main theorem, or one of the first main theorems that I talked about, was this elliptic parametric construction in this category. So in particular, you'd like to say if the symbol is invertible in the sense we described, then the operator is Fredholm. And that's not quite true, because you need and as in many types of boundary problems, there's sort of a hierarchy of symbols. So there's in fact a boundary symbol too. And it's actually an operator rather than the symbol, or an operator valued symbol. And I want to tell you a little bit about that today, because that will play a role as we go on further. Okay, so remember the picture that we had was this blow up. So this was the space M2, 0, which was my notation. I take n cross m and I blow up the diagonal of the boundary. Okay, so this was starting with this space, m cross m, right? I sort of had this submanifold of the boundary and coordinates around it, and then introduce the R equal error face. Okay, so there are many purposes that this has. And again, the point I really want to make is that everything we're doing, we really could do down here, but doing it up here just helps us see it better. So this is, if you like, you're trading sort of analytic complexity for geometric complexity. You have a space that's a little bit more geometrically complicated, but analytically simpler. Now, so I said that it's analytically simpler in the sense that the parametrices for elliptic elements live more nicely in this space. They're polyhomogeneous in this space. But let me actually show you how these operators live more nicely. So that's very elementary calculation. So the point is the following, that these operators, by their definition, are very badly degenerate at the boundary, right? So in particular, if I lift them up, so if I take L lifted to the left factor of m cross m, I have 2 copies here, and if I let L just act on the left factor here. So if I'm constructing the parametrics, I'm looking for some operator z tilde, and I'm letting L act on here, and I'm thinking of L acting in the z variable. That's all I mean by acting in the left factor, lifted to the left factor. Okay, and this is supposed to be the delta function of z minus z tilde. Right, so this is the type of operator I'm looking for. So let's do that, but now let's take the operator on the left factor here and lift it up to the blow-up. Okay, so now to lift up to the blow-up, I need to introduce coordinates. Now, I told you spherical coordinates, forward coordinates, whatever. And as you probably all well know from your first calculus course, calculating derivatives in forward coordinates is horrible, right? It's not really horrible, but it's not very pleasant. So instead, what we're going to do is introduce a set of what I'll call projective coordinates. So z is equal to x, y, z tilde is equal to x tilde y tilde, so x is the boundary defining function. And I'm going to define, so remember the submanifold we're blowing up is where x and x tilde are 0 and y equals y tilde. Okay? So the coordinates I want to introduce are s, which is x divided by x tilde, and w, which is y minus y tilde over x tilde. Okay? So what are these coordinates? Well, on this face here, so here's the sphere, all I'm really doing is take the tangent plane to the North Pole and stereographically project it. So it's a perfectly good projective coordinate system on this face, okay? So this is much nicer to compute with. So these are called projective coordinates. And the one thing which I want to point out, which is not obvious from this picture, is that, you know, if I have a general manifold, there's no God-given coordinate system. These x's and y's is just some arbitrary choice of coordinates, right? So there's nothing to say that something that's linear in x and y is linear in a different coordinate system, obviously. On the other hand, in these coordinates, if I were to change x to, you know, some other defining function, and x tilde would be changing in exactly the same way because they're the diagonal, tilde change. If I introduce these coordinates, well, they change, of course, badly, but a little computation, which I'll leave to your imaginations, is the following. That if I sort of change coordinates in the x and x tilde, y and y tilde, and then do this construction, and then restrict to the front face, I get just the linear transformation applied to s and w. Okay? So in other words, the projective structure I get on this face is completely natural. So this is not a smooth manifold, it's a projective manifold. So that's a very important thing. So when I write down something being constant coefficient or, you know, linear or polynomial, that really has an invariant meaning. Okay, so let's, in these coordinates, let's take the vector fields x d by dx, and let's lift it up. Well, so x is equal to s times x tilde. So the point is, in this coordinates, you know, really I'm thinking of coordinates x tilde, y tilde, s and w. So x tilde kind of measures how far away from the front face you are. Y tilde measures where you are on the diagonal of the boundary, and then s and w are coordinates on this front face. So really, this front face here, it's a little bit deceptive. There's a whole bundle of coordinates over the boundary, over the diagonal of the boundary. So there's a whole bunch of these coordinates here stacked up, parameterized by tilde. And these coordinates are bad at x tilde equals 0. So these degenerate at the bottom face here. Okay, so this is a good coordinate system everywhere in the interior, uniformly up to the front face, but not on the bottom.
So these coordinates correspond to that original picture.
This picture? This? Well, so x tilde is sort of a defining function for this front face, right? X tilde is 0 here, but then x tilde is equal to, excuse me, s goes from, so s goes sort of, it's a coordinate that goes down, and then w is sort of a coordinate that goes this way. Yeah?
So uniformly up to the front face, the front face intersects the right face.
Okay, so not uniformly down there. Everywhere else uniformly, but in particular uniformly along near the diagonal. So the diagonal stays a long ways away from this bottom face, and that's kind of the key. Okay, so if I lift these, if I lift x by dx, so x is equal to sx tilde, and then d by dx is d by ds, ds tilde is 1 over x tilde d by ds. And so here you see something that looks like s d by ds, x d by dyj are exactly the same computations as x tilde s times 1 over x tilde dwj, which looks like s dwj. Okay, so it looks like I made no progress at all because I still have these s's in front. Until I remember that along the diagonal here, along this diagonal, s is equal to 1 and w equals 0 here. That's the diagonal. So the point is that these lifts are completely non-degenerate near the diagonal. So you desingularize the problem. Okay? So in other words, these are non-singular near the lifted diagonal. Okay, and that's the big gain you can make. Okay, so what if I lift the whole operator down? So if I take this operator L, which is aj alpha of x and y, x and y to the alpha. So in these new coordinates, this is going to be aj alpha of x tilde times s, right? Y is equal to y tilde plus x tilde w. And then this becomes SDS to the J, SDW to the alpha. Okay, so here's this operator acting on this space. There's the diagonal. And so I have this operator that's acting on each sort of x tilde, y tilde equals constant slice, every one of these slices. Okay, here's the diagonal, sort of intersects this space. And what happens is this x tilde goes up and down. This operator is a perfectly nice differential operator, sort of in these horizontal variables, and it's not getting worse near s equals 1, w equals 0. Right, so in other words, this does not degenerate. Same ideas there. Does not degenerate near s equals 1, w equals 0. Okay, so in other words, I have this family of uniformly elliptic operators. It's not degenerating, but I've thrown in this tilde, so something's degenerating, but this blow-up has sort of prevented that from happening. Okay, so in particular now, what I want to do is take this operator L, lifted, so let's say lifted, and restrict to this front face. So this face here, I'll call the front face. Okay, so restricting to the front face just means I set x tilde equals 0. So this just means L lifted at x tilde equals 0, and here it is. It's the following sum, and let me write it out, j plus mod alpha is less than or equal to n still, aj alpha. So here I'm going to have a 0 y tilde, SDS to the j. Okay, so there's an operator. Now, let me make some comments about it. Y tilde is just a parameter here. It doesn't appear you're not differentiating with respect to y tilde. So basically, this is an operator with very simple polynomial coefficients, which depends parametrically on y tilde. The dependence is smooth, but this is just a parameter. Remember, y tilde sort of indexes where you are on the diagonal of the boundary. So you have one of these operators for every point of the diagonal of the boundary. And so this is a particularly simple type of operator. Now remember, again, this comment that I said that these projective coordinates are really natural. So if I change coordinates with x's and y's, the s's and w's, the s's and w's will change to something like, alpha s and beta, I forget what it is, so some matrix A of w plus, I forget, but anyway, something like that. Where alpha and a are constants. They depend on y tilde, for each y tilde they're constants. So in other words, these coordinates, and the fact that this has sort of monomial coefficients, SDS and SDW, is a completely natural statement. There's nothing coordinate dependent on. Okay. Now, the gain that you've made is you have this non-degenerate operator. It lives on this front face, which remember we've identified projectively with its tangent plane at the North Pole, and it has a lot of symmetries. So what symmetries does it have? It's translation invariant in W. So I can set W to W plus B, and I can dilate. S and W goes to lambda S lambda W. So this is, so these leave this invariant, this operator invariant. So this operator is in fact the boundary symbol. So let me give it a name. I'm going to call it N of L. This is the normal operator. And the way you should think about it, and so this is something that you don't typically tend to think of, but if you have a differential operator in a manifold and you freeze it at a point, you just restrict the coordinates to a point, you throw out the low order terms, right? You get a constant coefficient operator. Well, what you're really doing is so let's think about what you're really doing is if I have a curved manifold and I have some operator, I have a point I want to freeze coefficients at, really I'm sort of like dilating. Let's think if I have a P which looks like, let's say C sub beta dz beta, mod beta less or equal to m. Freezing coefficients here, really what it means is I lift it to the tangent space, I start dilating the hell out of it, right? So I replace z goes to lambda z, and I look at lambda to the minus m times the dilation, pull back, and this converges as lambda goes to 0 or infinity. You have to work out yourself for which, I forget. This converges to mod beta equals m of c sub beta at the center point, 0 let's call it, times d z to the beta. These are now, z is a linear coordinate on the tangent space at this point. Okay. So that's really what freezing coefficients on manifold for an operator is. I restrict to a point, dilate it, right? And this is the differential operator, which really corresponds to the principal symbol of the operator. So this is sort of a natural thing you can do to operators. And ordinary ellipticity says this is invertible, right? And you can understand an operator like this because it's just a constant coefficient operator on this vector space, right? So really, the standard elliptic condition is at any point you freeze coefficients in this sense, all of these models are invertible, then the operator is spread on a compact manifold. That's our old classical theorem. The new theorem is that if everywhere in the interior these constant coefficient models are invertible, and if this operator is invertible, this is sort of the boundary, this is the analog of freezing coefficients of boundary. Okay. Now, what's a little bit different is that this is sort of, this thing is now constant coefficient is formed out of a commutative set of constant coefficient vector fields. Just the d by dc commute with each other. These vector fields, STS and STW, do not commute with each other. So you can take kind of a group theoretic approach and say that these are left invariant vector fields with respect to some group. I don't want to do that, but that's kind of what's underlying the picture here. Okay, now, the theorem, before I state the theorem more carefully, let me just analyze. Yeah?
Sorry, at the top there where you have on the right, the L listed at that base, is that x hat equals 0?
X tilde equals 0.
X tilde equals 0, the right face?
No, the x tilde equals 0 is the front face.
But isn't that what it's degenerate?
No, that's the whole point. We're listening.
X total is in the denominator here.
X tilde is in the denominator, but the point is that on this front face, on this projected face, that x tilde is 0 there, and things don't degenerate there. Okay, so you just point out that this operator in an L, so it still looks like a partial differential operator, but you can actually reduce it quite a bit. So to analyze this thing, you still have to analyze something analytic, but something simpler. So if I take this n of L, which I won't rewrite, so there it is, it's translation invariant in W, so I can Fourier transform in W. So I can pass this to n hat of L, which is going to be the sum j plus mod alpha less than or equals m, aj alpha of 0, y naught, y tilde, and then I have STS to the j, and then minus I eta s to the alpha. Okay, so all I've done is I've sent dw to 1 over I times eta, or actually 1 over I, whatever it's supposed to be. Okay, so I've just Fourier transformed in that variable, and that's natural because it's translation invariant in W. And then I want to rescale. So then I want to set t is equal to s times the length of eta. I'm going to set eta hat is equal to eta divided by its length. And this thing transforms to, so sorry for all these symbols, I'm going to transform it to something that looks like this. So again, I have aj alpha of 0, y tilde, and this becomes t dt to the j minus it eta hat plus it eta hat to the alpha. Okay, so in other words, this is exactly the same operator as this, but I've done two reversible operations. I've Fourier transformed, and I've introduced the scaling. Okay, so what is this operator now? So it's a differential operator. So to analyze this normal operator, it's the same as analyzing this ODE. Okay, so that makes life a little bit simpler. And this ODE depends on two parameters, the y tilde, which is a smooth parametric dependence, and this eta hat, which lives on the sphere and the cotangent bundle. So really, this depends parametrically on the unit sphere bundle of the boundary. Okay. Okay, so here's the theorem. So if L is zero elliptic, so its zero symbol is invertible, and this Bessel operator acting on some weighted space. So let's suppose it's t to the delta L2, and this is just on R plus to t to the delta L2 of R plus, is invertible. So this is another type of ellipticity condition. So something else needs to be invertible. This is a statement about the symbol being invertible. This is a statement about this boundary operator being invertible. And it's relative to some fixed weighted space here. So if both of these are invertible, then L is a mapping from x to the delta L2 to x to the delta L2. And in fact, really one HM0 here is Fredholm. So the basic Fredholm statement requires two, the interior symbol and the boundary symbol. So remember I have the 0 symbol, so 0 sigma m of L, which is, I look at, whatever the operator was, I take just the top order terms and I take x dx, replace it by c, and x dy, replace it by eta. So I take this thing, which is the sum j plus 1 alpha equals m, aj alpha of xy exceeded to j, eta to the alpha. This thing. So this needs to be invertible as a symbol. Now, one other important comment. Notice I've thrown away all the lower order terms here. Here, I'm not throwing away the lower order terms. I have the order terms. So, if I have something that looks like, x squared dx squared plus x squared Laplacian y plus a times x dx, this term doesn't get thrown out. That's a top order piece with respect to the boundary symbol. I have let's say, a1 times x squared dx, that's low order. That gets thrown out in this boundary symbol. Similarly, if I have a 0th order term, c, which is non-vanishing, that's principal type of the boundary. That's a principal term. If I have an x times c, that's gone. Okay, so there's a different notion of low order at the boundary.
Why do you use the word 0?
Well, I don't know. I have to think of something. No, I think the origin of it was, so 0 just means things vanish at boundary. Maybe it's a stupid name, but there it is. It's been around for a while. Okay. There are other sort of parallel names for related degeneracies, so this is kind of in line with other things. Okay, so this is the basic. There, yeah.
Maybe I'm just confused. So real accent, these weighted spaces, what happens to the eta hat variable?
So you want to know that for every y tilde and eta hat. So this is supposed to be invertible for every y tilde and eta hat.
So this L2 space is in your t variable still.
This is only in t.
Yeah.
This is only in t. So eta hat and y tilde are just parameters. Okay, so there's something to be checked. And so in a certain sense, if you have a specific operator that's kind of a big operator, like the elasticity operator, or the Hodge Laplacian, or the Lick-Narowitz Laplacian. So there's a lot of applications in this theory. At the end of the day, you have to analyze this ODE, and it may be terrible to do, or impossible, or difficult, or whatever. So you have to analyze this model problem to understand Fredholm's. Okay, now what is delta? So yeah.
Because you always have, like, in the boundary, we have 0, but there is a constant that is not cancelled, right? Because we have this C0 there.
Right. So the point is that that's that will affect things. I mean, so one reason to think why that's a principal term is suppose I take L acting on a term that looks like x to the gamma. About in this for additional complications. So there's going to be a bunch of junk involving x to the gamma plus big O of x to the gamma plus 1. Stuff that gets piled up here is the x to the gamma bit. That doesn't, but that does. So, of course, that's not analysis, that's just algebra, but somehow that's really affecting things. Okay, now I said if there's some delta, so let me just mention what deltas we typically have to consider and what happens if, well. Okay, so what's delta here? Well, so remember we had these indicial roots. So we had L had this indicial roots. Down over here, the stuff multiplying x to the gamma. When I sort of take L applied to, an arbitrary function of y times x to the gamma, I get a bunch of junk times x to the gamma plus higher order vanishing stuff. And the indicial root, gamma is an indicial root if that leading coefficient vanishes. It's a polynomial condition. And it's an mth order operator. It means it's an mth order polynomial. So I have these m initial roots. Okay. And I can now look at weights. So I'm going to call these weights delta j, so that x to the delta j L2. So I want to choose weights. So here, so that x to the gamma j plus epsilon is in, and x to the gamma j minus epsilon is out. So by which I mean is for every single gamma j, I look at weighted spaces near 0, near x equals 0, so that, you know, this is right the borderline L2 weight. So if I make the weight a little bit higher, you lie in this weighted space. If you make it a little bit lower, it's out of that space. Okay, so then here's the delta axis. So if I look at the space of weights, there's going to be n weights here. And so the basic fact is that if this operator is invertible, that actually is only going to happen in one of these intervals, if ever. So there's going to be one of these intervals where it's invertible and nowhere else. Okay, now you might ask, what happens at these bad weights? And I call them bad because bad things happen. And what happens in these other intervals? Okay, so at the weights itself, so what's true is that L at actually these bad weights does not have closed range. Okay, so that's terrible. Okay, and what happens when you're at one of these other intervals? Well, so there's a slight generalization of this theorem, which says that if this ODE is not invertible, but let's say it's surjective, but not injective, then the corresponding operator is almost surjective. It has only a finite dimensional cokernel, but it'll have an infinite dimensional null space. And so what happens here is as I move to these intervals, as I go forwards and backwards, if you move this way, you pick up a bigger and bigger null space. So what happens is that if you're looking at spaces of functions which blow up worse at the boundary, as delta gets more negative, you're going to develop an enormous infinite dimensional null space, but you're going to become surjective. If you go this way, the opposite happens. You're going to develop an enormous cokernel, infinite rank cokernel, but no null space. Okay, and let me just point out that this is a phenomenon you're basically familiar with. It was not often referred to. Suppose I take x squared times dx squared plus velocity y. So this non-degenerate operator multiplied by x squared. The initial roots here are 0 and 1. Those are the two initial roots in this non-degenerate case. So you're going to have two, and depending on what measure you use, let's say the thresholds are exactly the same, 0 and 1, just for argument's sake. So 0 and 1. Okay, so being in a weighted space right here. So suppose I look at this operator acting in a weighted space between 0 and 1. That corresponds to demanding that the x to the 0 coefficient is common. That's a Dirichlet condition. And so what you know then is that you get a Fredholm problem. So this corresponds to the Dirichlet problem. Okay. On the other hand, I have this two semi-infinite intervals. So for example, I might be letting this operator act on x to the delta L2 to x to the delta L2, where delta is very negative or delta is very positive. What happens in those two cases? Well, when delta is very negative, I'm allowing in all sorts of functions which are non-vanishing at the boundary. And there's lots of bounded harmonic functions. Right? So the point is, there's clearly an infinite dimensional null space if I allow in functions which don't decay at the boundary. Just all the harmonic. Right? So there's a big infinite dimensional null space. Then it becomes nice and Fredholm. And then if I go the other way, there's sort of the dual picture where I have an infinite dimensional cokernel. So again, that's not a picture that people typically think of, except for that people study bounded harmonic functions like that. So in this whole theory, there's an analog of this for any zero-elliptic operator. Okay, you might ask, what about the Neumann condition? So the Neumann condition corresponds to sort of including things that have that, but excluding this. So, you know, that's kind of a more complicated boundary condition. I don't want to talk about this today, but you can do that as well. Okay. So anyway, this is the type of theorem that you get, that you have, you know, Fredholmness in some range, very badly non-Fredholm, but possibly semi-Fredholm, so the infinite dimensional kernel or cokernel, but the opposite, the cokernel or kernel or finite. And when you go in sort of intervals like this. And, how this works out, well, you just have to analyze that operator. So, for example, for the Lichnerowitz Laplacian for conformally compact manifolds that Alice has been talking about, you have 4 weights, I think. Fortunately, there's sort of a nice Fredholm interval in there. But then you're going to have this interval here where you're admitting sort of a bunch of stuff which is blowing up the boundary, which actually, here it's sort of gauge terms, and over here, that corresponds to changing the conformal structure of infinity. There's multiple definitions of that. And you go here and the cokernel becomes bigger and bigger. So often for geometric operators, these initial roots have very specific geometric meanings. Okay. There are other stories. For example, there's a situation where the 2 initial roots might be a second order operator. The 2 initial roots have the same real part. So then you're in a really weird situation where the operator is never Fredholm. Right? So over here it has infinite dimensional kernel, over here it has infinite dimensional cokernel. And an example of that is if I take, so this operator, Laplacian u plus u to the p, so actually Martin and I have been studying a version of this now, but this is old work I did with Frank Picard. If I look at this sort of Yamabe type operator, you linearize around the basic solution, u is equal to r to the minus 2 over p minus 1. So this is, let's suppose that here's a submanifold, and r is the distance to the submanifold. So it's out, if I take this operator, linearize around this, it turns out that I'm in a situation where I'm never Fredholm. And there are lots of solutions to this equation, but in fact, because the linearized problem has an infinite dimensional null space, and I work on this way, the nonlinear problem has an infinite dimensional null space. Or, set an infinite dimensional space of solutions to this. Okay, so, that can happen in geometric problems. The Yamabe problem. Okay, so any questions about any of them? Now, let me tell you, so this is, sort of in reasonably good outline, the theory of zero elliptic operators. So let me tell you about some other degenerate situations that one can analyze, and we'll finally get to this case of the fractional Laplacian and banded domains. So a case which was kind of studied in a sense earlier than these zero problems was what are called, so suppose I have an operator on an infinite cylinder. Suppose I have a manifold with an infinite cylindrical end. So I have a metric, and it looks like, dt squared plus h, where t goes to infinity. There's t. Okay. Now, remember what I said, that the steps are you compactify, then you blow up stuff, and then, continue. So compactifying here corresponds to letting x be e to the minus t. So namely, I want to think about this as a compact manifold with boundary, right? And the operator d by dt squared plus Laplacian h becomes x d squared plus Laplacian h. So I have a boundary now. Here's x and here's y, and so this is a different type of problem, okay? And a different sort of degeneracy. So here the degeneracy is only the normal variable degenerates, but the tangential variables don't. Okay, this corresponds to cylindrical geometry, asymptotically cylindrical geometry. Okay, so this is called the theory of B elliptic, elliptic operators. Well, elliptic if you have a certain condition. And so B stands for boundary. That was the origin notation. And so this was really the first case it was studied. And this was, so Melrose encountered this, and he was actually working on a non-elliptic problem. He was working at diffraction of wave equation, solutions of wave equations at boundaries. This was sort of this famous work he did in the late 70s or early 80s. And he kind of realized that these considerations turned out to be very effective for understanding diffraction problems. And that was a very important sort of bit of progress in hyperbolic equation theory. And then there's sort of a whole elliptic story that followed. Okay, let me just sketch a very small number of things. So there's going to be analogs of everything that we do here. Okay, so here's the degenerate operator. If I take m cross m, again, I can draw it as a picture like this, and I want to just want to emphasize a couple of points when I do this. The dy coordinates are not degenerating. So if I do something like I did before, if I blow up to make something singular, it was non-singular to start off with. If I do a blow up which involves the y coordinates, I get into trouble because it becomes degenerate. So in other words, what I want to do is just blow up the x coordinates, but not the y coordinates. So in other words, the correct blow up here is this. So this is called M2B. So I've blown up the whole corner. Okay. And well, one can go on and sort of study these things. So there's going to be a model operator, there's going to be additional root. And the real case is that now there's infinitely many additional roots. So what is sort of the problem of additional roots? So if I take this operator L and let it act on x to the gamma phi of y, I'm going to get, in this particular case, gamma squared plus Laplacians of A acting on phi plus big O of x to the gamma times x to the gamma plus big O of x to the gamma plus 1. So I'm doing the same thing. I try to put in an x to the gamma times some function. This is the leading coefficient. And now there's something very different that happens. I get some junk, but it's differential. It's not just algebraic. So remember, in the zero case, I got a polynomial. Here I get an operator. So what happens is that this is bad. Precising gamma squared is an eigenvalue, the boundary Laplacian. So the point I want to make is that this theory is now global on the boundary. So in other words, I see the operator on the boundary, and I see its entire spectrum that appears in the mapping properties. So whereas before in this zero theory, it was just purely local on the boundary. Okay, so there's going to be now infinitely many additional roots, gamma j, and z. They go in both directions, gamma j is s quadratic. And I'm going to have the following sort of picture. So if I let it act, there's infinitely many bad weights where the operator is not Fredholm. And what happens in between? Well, fortunately, it's a little bit better than what I said before. Namely, it's Fredholm in every one of these intervals. Right? There's a jump, and you can actually calculate the jump of the index as you move back and forth. But it's Fredholm for every weight which is not one of these threshold weights. Okay, so that's another whole picture, another whole story that one can develop. As something that's a mixture between the zero and the B type problems, which are called edge problems. And they're called edge because they correspond to the following sort of geometry. Suppose I take a bundle of cones. Now, what I did was I took a cylinder, but I could have equally well taken a cone. The point being that the Laplacian in a cone just looks like 1 over x squared times this. So conformally, cones and cylinders are the same. And so the corresponding operators are essentially the same, up to a factor. Okay, so if I want to analyze conic singularities, this is the right theory. Okay, and it corresponds to having a bundle of cones. And a very classical example of that is suppose I'm in a manifold and I have a submanifold. And I introduce cylindrical coordinates around it. So you can think of this now as a theory of sort of higher codimension boundary problems. Namely, suppose I'm looking for harmonic functions which have a special behavior along a codimension 2 submanifold, for example. Now, how does this look like this? Well, if I introduce cylindrical coordinates, I have the cross-sectional variable, right? The spherical variable here, and then I have the variable here which corresponds to moving along the edge. So the point is that this is a blend of the edge and the zero problem, the edge and B problem, the zero and B problem, I'm sorry, where this is sort of like the zero problem I've been talking about in such great length, and this is like the B problem that I just mentioned very briefly here. So they both are living in the same picture. Okay, so where does this go? Now I'm going to mention one, so there's many different generalizations we pursued over the years, depending on various geometric situations. Let me mention one that's very general, and which is going to encompass the thing I'm quite interested in, which we'll get to in 2 minutes. Okay, so what I'm going to call iterated edges. So an iterated edge, well, in general, it's basically when you do a repeated process. So suppose you have a space that you know everything about, like a compact smooth manifold. Here, what I did was I took a compact smooth manifold, took a cone over it, and then took a product with a Euclidean space. Or more generally, took a bundle of cones over that compact smooth manifold. So I get a space that has some sort of edge, but this is some sort of edge here, but it has some sort of singularity. Now suppose I repeat the process. I take a cone over that and take a bundle of things like that. So how should I think about that? Well, here's kind of a nice picture. Here's a space with a conic singularity. Right? So I can draw that, that's not too bad. And then suppose I take a cone over that. Okay, so what happens here is I have a whole edge, which is sort of the conic stratum over that isolated point. And then I have this new conic point, which is worse because it has this edge coming into it. Okay? So the iterated edge picture looks like this, except I can keep on drawing 25 times. Okay, why would I want to do something like that? Well, there's a class of spaces that you know, which have this behavior in polyhedron. If I take a polyhedron, this is an iterated edge. So if I think about, let's say a cube, right? Well, what this is going to do, near the boundary, it's looking like a cone over a triangle. So I take a triangle, I take a cone over the triangle, and that's sort of the corner of a cube. Okay? So in other words, one of the things that we're interested in pursuing is how do you do analysis on polyhedron? Right? So, as you all know, you can do sort of, let's say too pejoratively, crude analysis on polyhedra by, use energy methods and you get stuff. But if you want to sort of understand in a very detailed way, if you have harmonic functions on a polyhedron, what do they look like near the corners and boundaries? And there's a lot of interesting geometric problems where you need to know fine asymptotics as you go to the corners. So let me give you an example of that, which is really the conic case, but it's kind of one that exhibits behavior that we know. From other considerations. So let's suppose that we have a square. Let's suppose we have a square. And we look at, let's take something a little bit better than let's suppose I take an eigenfunction on the square. Right? And I can ask, and let's say phi restricted to the boundary is equal to 0. Okay, what does it look like? And in fact, to make life easy, let's not make it a square, let's make it okay? Okay, who knows the answer, how this behaves near the corners? Anybody? Okay, well, it's nice and smooth as you come in here. How does it look in these corners? Well, I can sort of draw a localized picture. It's going to be looking roughly like this. And in fact, in polar coordinates around this thing, it's looking like some r to the gamma times some psi of theta, where the psi is an eigenfunction interval. So I have this interval in theta going from 0 to theta naught, depending on the angle. Just d theta squared on this interval with Dirichlet boundary conditions. It has some spectrum, which you can figure out easily enough because that's a one-dimensional problem. So I have some spectrum on the d theta squared here. And then these gammas are going to be the initial roots corresponding to this spectrum. So this is a conic problem, right? And I'm going to have these gammas, so phi j tends. And so the point is, I'm going to typically get solutions which kind of bulge here if the cone angle is less than this. So I've always thought of this as a nice mathematical theorem. And my father-in-law, who's a numerical analyst, once said, oh, well, that's why the tides are so high right near Mont Saint-Michel, right? So, if you look at the coast of Brittany, right, there it is, there's Mont Saint-Michel, and the tides are very high there, and it's exactly that phenomenon, which is pretty cool. Well, it's kind of idealized. Okay, so the same thing happens with polyhedra. You can analyze, yeah.
Question. Does the decay or the power of R depend on the angle of the
Yeah, absolutely. Yeah, so if you take a very narrow angle, it bulges up a lot.
Okay.
Yeah, this is a very elementary calculation, right? Just separation difference. Okay, so anyway, you want to do analysis on polyhedra and get fine asymptotics in corners. You need to do something sophisticated, and this is sort of a tool to do it. There are other tools, but this is a tool to do it. Okay, so okay, finally, fractional Laplacians on over here. Fractional Laplacians on bounded domains. Okay, so let's now finally look at this. So I should say this is work I'm doing this year. Well, the past few years because I'm slow, but this year with Heiko Gimperlein and Nicoletta Luca. And Heiko has the nice feature of being both a microlocal analyst and a numerical analyst. So he came to me with sort of very specific problems. And what he was actually interested in was fractional Laplacians and polyhedra. And I said, okay, that sounds like a great problem that we can probably do. But we realized we need to understand fractional Laplacians on just smoothing the boundaries first. Now, of course, a lot of people have done that, and I'm not going to cite the literature because I think many of you are much greater experts on this than I. So many people, Rosaton and Sarah, and so many people have done analysis on the fractional Laplacian on domains of boundary, but I wanted to just talk about a different approach to it, which is based on these sort of ideas. Okay, so remember that we have this sort of Caffarelli-Silvestri picture. I take this operator, d by dt squared plus 1 minus 2s over t dt, plus Laplacian in the x variable, so this is the x variable here. And I look at the following problem. So to solve Laplacian to the s of u equals f, this is the same as the following situation. I find a solution u of t and x, where L sub s of capital U is equal to 0. Capital U at t equals 0 is equal to little u. And then the Neumann condition, so this is t to the 1 minus 2s dt of capital U, limit as t goes to 0, is equal to f. So I can read this backwards or forwards. I can say, pose u, doesn't need to have a domain or boundary here, just take it on our end. I pose a little u, solve the Dirichlet problem, namely, find a solution to this degenerate equation with that leading coefficient, right? And then take its Neumann condition. If I want to solve Laplacian u equals f, where I know f, I solve the Neumann problem, right? I pose f, I find a solution capital U which does this, and then I take its boundary. So that's the Caffarelli-Silvestri approach. Now, where that comes from is, and it's worth understanding if you haven't seen this before. So where this comes from is, if I look at this operator, let's just Fourier transform the capital X variable. So this is going to correspond to dt squared plus 1 minus 2s over t dt minus mod c squared of u hat. And this u hat is of t and c is equal to 0. So I'm just Fourier transform. It's not formally doing this, right? I'm just assuming that things are decaying as state infinity. Okay? So I take the Fourier transform of the capital X variable. This is just an ODE, it's a Bessel function. I mean, it's a Bessel equation. So the solution looks like, I forgot to write it down, but it's going to be, the solution is going to look like k, hold on, I know this, t to the minus s, k s of t minus c. That's a guess. So I'm probably wrong, but I think that's that. So this is the k Bessel function. So k sub s, this guy, if I look at k sub s of sigma, this looks like sigma to the s is sigma goes to 0, and it looks like e to the minus sigma over root sigma as sigma goes to infinity. Okay. Multiplying by, oh, shoot, that should be a t to the plus s. Sorry. Yes. Okay, so what this solution does is it looks like t to the 0th power as t goes to 0, and t to the 2s as t goes to infinity. Yes, sorry. No, excuse me. That's not what I wanted to say. Sorry, and e to the minus t over ut times the t to the minus 1/2 s minus 1/2 as t goes to infinity. The slightly more important point is what's the higher order asymptotics of this guy? So if I look at t to the s times k sub s, t minus c, this looks like, so let me write it as a of c times t to the 0, plus a bunch of junk, plus b of c times t to the 2s. So this is the asymptotics of this. We call this a0 and b0. So remember, any solution of a zero elliptic problem, this is zero elliptic, has an asymptotic expansion. This is just the ODE case, which was known to, I don't know, Fuchs, whoever else in the 19th century. This is sort of the asymptotics as a function of t. The coefficients depend on c. And what you can easily check is that if I pose any a naught of c, I get a solution, which decays exponentially as I go to infinity, which means I can take its inverse Fourier transform. If I have the exponentially increasing values, I'm screwed because I can't take the inverse Fourier transform. Okay, so I want exponentially decreasing solutions. So it means I can pose this guy any way I want, and then whatever A naught of C I pose, I'm just going to be stuck with some B naught of C. It's whatever it is. And in fact, this B naught of C is up to some factors which depend on S. This is equal to some coefficient times mod C to the 2S times A naught of C. So that's sort of an easy calculation. Okay, so in other words, at the level of the Fourier transform, I'm just multiplying by mod C to the 2S. Once I take inverse Fourier transforms, that corresponds to Laplacian to the S of A. Okay, so that's the Gimperlein semester. S between, you can do this for any S right now. I'll stick to S between 0 and 1 because certain things work out much nicer, but in principle, you can do this for any S. There's a general. Yeah. I mean, but various things go wrong when S is, I mean, you know, things get more complicated when S is bigger. Okay, so in other words, this Gimperlein-Sylvester theory is really just a special case of the zero elliptic theory. And the Dirichlet-Neumann mapping in this context is exactly the fractional Laplacian. We've seen that already with the scattering operator. And notice that, you know, capital U at T equals 0, which is inverse Fourier transform, is just the inverse Fourier transform of A naught. F, which is the Neumann condition, well, if I take d by dt, it's going to give me a t to the 2s minus 1. And I multiply by t to the 1 minus 2s, and I take the limit, I get the B naught. So in other words, these two conditions just kick out the A naught and the D naught automatically. Okay, so what are the problems that one would like to pose now when we have not functions on the whole space, but we have functions just on bounded domain? Okay, now I'm going to idealize the picture right away because it's easier to draw, which is here's my domain, here's omega complement. Okay, so really, of course, you know, I'm thinking of a picture like this where here's omega and then it's outside. But I'm just, you know, freezing coefficients. So by now you should be convinced that this is a coordinate invariant theory, so you can take coordinates to flatten out stuff and so on. These computations are very hinged to the Euclidean coordinates. But of course, once I set it in this bigger microlocal context, I can curve it as much as I want.
So your omega now is
This guy.
y
Is what? This is t equals 0. This is the plane t equals 0. Okay? So I'm going to do exactly the same thing here, but now let me point out that there could be 4 problems that I'm interested in. So namely, I could be looking at u at t equals 0 in omega, or u at t equals 0 in omega complement, t to the 1 minus 2s dt of u at t equals 0 in omega, and dt t to the 1 minus 2s dt of capital U on at t equals 0 in omega complement. So I have 4. So this is Dirichlet inside, Dirichlet outside, Neumann inside, Neumann outside. Okay, so in other words, if here's my domain, I can pose either Dirichlet or Neumann on this side and either Dirichlet or Neumann on that side, and that's an interesting problem. Okay, so the classical thing that you might have seen is that I pose Dirichlet inside here and make it 0 outside. But there's no reason, in fact, there's a lot of good reasons to consider any one of these combinations. Okay, so a special case of this, which I mentioned just very briefly the other day. So there's a classical problem that goes back to 1910 called the Zaremba problem. Which is, suppose I have a domain. So this is a local problem now. So the Zaremba problem says, suppose I have a domain. It could be in, well, let's take it in R3 or something like that. So I have a domain, so it's like the interior of this egg, right? And I split up the shell, split up the boundary into 2 bits. So I'm going to have boundary minus of omega and boundary plus of omega, of these 2 bits. And what I might do is solve Laplacian u equals f in omega, and then u restricted to boundary plus of omega is equal to phi, and dn of u restricted to boundary minus of omega is equal to psi. So that's the Zaremba problem, right? I sort of split up the boundary into 2 bits and pose Dirichlet on one side and Neumann on the other. Or you can do a lot of variants. You could put Dirichlet here and Robin conditions there, or blah, blah, blah. There's a million combinations. But Zaremba thought about doing this. He had some specific applications. The geophysicists love this problem. This comes up all the time in geophysics. Okay. So, you know, you can solve this just by energy methods. I mean, there's sort of a Dirichlet form, and you know, you can do the normal thing. But then, if you have a certain turn of mind, like mine, you ask, what's the precise regularity near this, right? And so let me flatten this out. So here's the interface. Here's boundary minus omega, boundary plus omega, and here's the interior. So, you know, when in doubt, don't integrate that part, you blow up, right? So I'm going to blow up this interface. Okay. And so here's a theorem which special cases have been known for a long time that it sort of follows from what I talked about here. I don't think it's ever been written down specifically, but it's true. Suppose I have this problem, and let's suppose just for simplicity that f and phi and psi are all smooth. Okay, so if f, phi, and psi are all C infinity, just for simplicity, then u on omega exists. How smooth is it? Well, it's obviously smooth up to the boundary here. That's just local classical boundary regularity. What does it look like near here? It's smooth, well, polyhomogeneous on this blown-up space. So U is polyhomogeneous on the blown-up space. Okay. Now, what's new about this? Well, the polyhomogeneity. What's new is exactly the behavior as I come to this interface. So I'm in an omega and I'm coming to the interface in various directions. And what this interface has is it has a bunch of semicircles. These just correspond to sort of, you know, the inward pointing normal spherical bundle there. The operator, if I write it in cylindrical coordinates around here, there's going to be some sort of d theta squared term here, and I take the eigenvalues of that. So namely, this is one of these edge problems where I have, so this is just like what I was talking about, you know, with the versus Normandy up there. So you have one of these edge problems. It's parameterized by points on the interface. You have the eigenvalues of theta, and those are going to determine, so I'm going to have like r to the gamma j times phi j theta. These gamma j's are going to be whatever the boundary conditions are. So in particular, I have the interval, and I have Dirichlet on one side, and I have Neumann on the other. That's what this Zworski problem tells me to do. I take the eigenvalues of that problem, they're whatever they are. They're pretty simple in this case, because the angle is pi. And I get the initial roots, and that's what the exponents are in this expansion. Okay.
So you miss the expansion, do you have just logs them also?
You might or might not. You know, the logs are kind of, you know, they're there as annoyances, but they're not very serious. So there might be there. They're probably not in this case. Sometimes they do. Okay, so why is this interesting? Well, so again, you know, geophysicists are interested in doing numerical work, and it's nice to know sort of what type of asymptotics you expect as you get towards this interface. Okay, now I told you a very big simplifying assumption where these guys are all smooth, and I get polyhomogeneity. What happens if they're only polar continuous? Something like this. Okay, so let me write down what the cylindrical coordinates are here. And I say all of this, remember, this is a local problem. I'm going to go back to this global problem in just a moment. The statements are going to be essentially the same, but it's a little bit of a different story. So, and of course, this is a special case when s is equal to 1/2. So here, I'm going to have y, which is a coordinate along the interface, along the crack, right? Here I have theta, and then r. So these are cylindrical coordinates. Okay, so this statement of polyhomogeneity means that u of r, theta, and y. So here's sort of the general expansion theorem that I talked about before. I'm going to get an expansion in powers of r to the gamma j, where these gammas are determined by the spectrum of this operator on the cross-section, times some coefficients, aj of y and theta. So this is now a general asymptotics theorem for solutions of this Zworski problem, no matter what the regularity of f, y, and psi are. Okay, well, let's suppose that f equals 0, just to make life really simple. But so what do I know about these AJs? So they're smooth in theta. For each J, they're smooth in theta. They're essentially just these phi j of thetas. They're smooth in theta. But they're very badly distributional in Y. Okay, now, the precise statement of that, which is what's interesting, the precise statement depends on what sort of function spaces you want to measure things in. So let's use Sobolev spaces, for example. And again, there's sort of analogs of these for any choice of function spaces like Boulder or whatever. Okay, so this operator, if I write it in these cylindrical coordinates, is built out of the vector fields r d by dr, r d by dy, and d by d theta. These are sort of the edge vector fields. Okay, and so the operator itself is built out of just, it's a sum of squares of these things, essentially, times 1 over r squared. The Sobolev spaces that you're interested in are built out of these. Okay, so in other words, I take Sobolev spaces, let's call it HK edge, which is the space of functions u such that RdR to the I, Rdy to the alpha, d theta to the beta of u is in L2. This is for I plus mod alpha plus mod beta is less than or equal to k. These are the appropriate spaces to use. Now, of course, why do I say appropriate? These are the easiest spaces to use because they're sort of adapted to the geometry of the problem. Okay. So the easiest theorem you can prove is that the solution, so here's a general theorem. So let's suppose that Laplacian u is equal to 0, u at boundary plus omega is equal to phi, dn of u on boundary minus of omega is equal to psi. And let's suppose that phi and psi live in some of these Sobolev spaces. These are theta is equal to 0 or pi. So these are going to live in, let's say, HK 0 of omega plus or minus. So the 0 means I eliminate this guy. So I just have r and y on either side when I'm on the boundary. Okay, then u is going to live essentially in HK plus 2 edge and this is boundary, and this is in the interior omega. So in other words, if I have this scale, so what's nice about these spaces is they're invariant under dilations locally. So if I have these guys, they're invariant under dilations on the boundary, excuse me, if you have this sort of norm where it's invariant under dilations in the boundary, then the corresponding u gains 2 derivatives with respect to that degeneracy structure. Okay, so that's a very precise and sharp theorem. Right, and so another way to think about that is, again, let me sort of do this blow up. Another way to think about that is that as I go towards here, phi and psi, so I have phi and psi on these two sides, u is going to be sort of have whatever Sobolev regularity up to the boundary. That's classical elliptic boundary theory, here and here. As I come along here, what happens is that it's nice and smooth in the theta directions, but in this direction, it has this, it can become very crinkly. It can become very oscillatory. And that's just a fact of what solutions do. But this measure is exactly, these spaces measure exactly how oscillatory it gets. Okay? When I say oscillatory, this is sort of a statement that, you know, let's suppose I use these x and y coordinates. You know, this kind of regularity is saying if I'm stable regularity with respect to x dx and x dy, 0 spaces, that means that for a given level x, it's nice and smooth, or has, you know, k derivatives. But as I get closer to x equals 0, it can be oscillating so long as its oscillations are of size 1 over x, right? And this is exactly what harmonic functions do, right? Harmonic functions in general, without boundary conditions, they're nice and smooth when you're a long ways in the interior, and as you get towards the boundary, they're oscillating at size 1 over x, where x is the distance to the boundary. So this is, you know, been known since time immemorial, right? And this is measured by Whitney cubes and stuff like this. So that's kind of a very classical harmonic analysis picture. So this is a generalization of that. Okay, so that's the classical Zaremba problem. And the only difference with the thing I really want to talk about is that the interior operator is just the garden variety Laplacian. Okay, so with this fractional Laplacian, the only difference is I have Dirichlet, Neumann on the two sides, but the operator in the interior is one of these degenerate elliptic operators, this L sub s. So it's the same story. I have an interface, and I have either Dirichlet or Neumann on the two sides, and I'm trying to solve L sub s of capital U is equal to 0. So I'm trying to find homogeneous solutions which have either Dirichlet or Neumann conditions prescribed on the two sides. And the question is, what's the sharp regularity of that? And so what that comes down to, so now let's get to a little bit more nuts and bolts. I can prove a theorem like this. So what I really am interested in is a set of Poisson operators. So really, I would like to understand what are the Poisson operators, and I have three Poisson operators to be interested in. P Dirichlet, P Neumann, and P Dirichlet. So I have Dirichlet on both sides, I have Neumann on both sides, or Dirichlet on one side, Neumann on the other. Okay, so in other words, I'm interested in, if I put in a pair, P plus P minus, phi plus phi minus, let's call this phi's, and let's say phi plus and psi minus. Where the phi's are Dirichlet and the psi's are Neumann. Okay? So what I would like to understand, if I put in a phi here and a psi here, what's the behavior? Right? So a simple case of that is where I have Dirichlet, and right, so I have phi minus here, phi plus here, and so really, before I do the blow-up, that just means I have a piecewise smooth function, for example. Suppose I take the data, Dirichlet data, which has a jump on an interface. So that's a special case of what I'm doing here. When I have Neumann, I just jump in a more complicated way with normal derivatives. Okay. So really, what I'd like to do is understand those Poisson operators. So that's kind of the name of the game here. I want to understand these Poisson operators, and then look at their mapping properties. So when I prove these types of theorems, that really is a statement of, I construct these Poisson operators as elements of sort of an iterated edge calculus, and I understand their mapping properties. So that's the strategy. So let me just tell you a few things. I think I'm not going to get too much into details here, but let me just tell you a few facts. Okay, so let me tell you what the Dirichlet Poisson operator is, because it is just the Poisson operator which I'm applying to piecewise discontinuous data, piecewise smooth data. So here's the Dirichlet Poisson operator. So PD of T and X tilde. Okay, so here it is. So it's 4 to the S. So here's the powers gamma of n over 2 plus S divided by gamma minus S times pi to the n over 2. So these are just harmless factors. And have T to the minus n times 1 plus mod x squared over T squared to the minus n over 2 minus S. And Neumann, excuse me, this should be x minus x tilde. So this is going to be similar sort of factors, n over 2 minus S over 2s gamma of minus S, pi to the n over 2, t to the 2s minus n, 1 plus mod x minus x tilde squared over t squared to the minus n over 2 plus s. Okay, so how do I get these? Well, it's really, it's been known forever. It's a Fourier analysis, and you're taking inverse Fourier transform of whatever you get. There's no interface inside of it, right? So the interesting question from our point of view is, if I take this piece of D and I apply it to, so I'm doing the following piece of D of T x minus x tilde, and I apply it to some phi of x tilde, x tilde, where this phi has this jump property, phi plus and phi minus, and this is in, so if I let x be equal to xy, or x is an r, and y is an r minus 1, this is phi plus and x positive, and phi minus and x negative. Okay, so I just take boundary data with a jump discontinuity. There's phi minus over here, phi plus over here. I want to know, what does this kernel do when I do that? Now, in fact, you can just stare hard at this integral with these explicit expressions, and you can get this polyhomogeneity I talked about, or this, this edge regularity. The reason is, if you look at these expressions, they blow up nicely, right? So in other words, if I write these in spherical coordinates, so if I write t is equal to, let's say, r times omega naught, and x minus x tilde is equal to r times omega primed. So here r is equal to root t squared plus 1 x minus x tilde squared, and omega is equal to t x minus x tilde divided by r. So these are spherical coordinates. So what are these? These are spherical coordinates around the diagonal of the boundary. Okay, so if I have x, x tilde, and t, that's where the Poisson kernel lives. I have the diagonal at x equals x tilde, and I blow that up. And in terms of those coordinates, these are going to look like very nice functions. So let's compute that for, let's say, the Dirichlet guy. So there's going to be some coefficient of s. T to the minus n is r to the minus n, omega naught to the minus n. Then we have 1 plus omega prime squared over omega naught squared to the minus n over 2 minus s, which I'm going to rewrite as c of s. And now let's see. So the r's have gone away. So there's exactly a power of r to the minus n here. And then if I take this omega naught squared, let me see, it's going to give me omega naught to the 2s times omega naught squared plus omega prime squared to the minus n over 2 minus s. Well, that's one. That's on the unit sphere. So there it is in spherical coordinates. It could not be simple. It's just a power of, so here's the spherical coordinates. Here's omega. Omega naught is that vertical direction. Projected by omega prime is this direction. Right? And here r is the defining function for the space. The Poisson kernel is just a power of r. Why is it r to the minus n? Because you want it to be the delta function at r equals 0. Times a power of the defining function for this boundary here. And that's it. You can do that with the ordinary Poisson kernel in Rn too, just the one that for the ordinary Laplacian. So this is for this degenerate Laplacian. Okay, so this kind of at least vindicates, or at least exemplifies exactly the theorem that we like to say, that each of these PDDs, PNN and PDN, are polyhomogeneous in some appropriately blown up states. Okay? Now, I've just written down PDD and PNN. It's just these two kernels lifted to this space. What is PDN? So that's the hard guy to get to, and that's the one you're often interested in. So we have Dirichlet on one side, Neumann on the other side. And so that you cannot write down an explicit formula for because it doesn't have a homogeneity that allows you to produce fluids. Excuse me? This corresponds to PDD. That's exactly right. So for PDN, the mixed problem, it's not homogeneous, so you can't just reduce it to an ODE. These guys you can, which is why I've written down explicit expressions. So that's a long story, unfortunately. I'm not going to tell you about it. But roughly speaking, here's what you do. I take a phi plus here and a c minus here. Okay, I take PD and I extend it. I use it to extend phi plus off of this side, and I cut it off. So I have a good solution over here, which is given by taking the Dirichlet Poisson operator and cutting it off to the sector. I take the Neumann Poisson operator applies a psi minus, and I cut it off to this sector. So now in this picture, I have sort of a good solution here and a good solution here, but I have to correct these here. Okay? So I have to look at Green's function. So unfortunately, this is a more complicated story. To get the Poisson operator, I have to understand the Green function in the interior with zero boundary conditions on the two sides. So I construct that via a big parametrics construction, and we get proper asymptotics, and this is what follows out of it. So that's, I think at the level of detail I think is dignified to talk about in public. That's probably all I want to say about this. I do want to just comment on a few things which I think will be possible. And I think, so this is, in some sense, this is known from other points of view. And again, there have been many really brilliant people who worked on this. Yeah?
Sorry, maybe ask the question, but in the Dirichlet-Neumann case, don't we need any compatibility condition?
No, that's the point. It's like if you have a piecewise smooth function. They're not compatible. So, what the function...
Yeah. I mean, the thing is that, Neumann is invariant under some, under some inconstants. So that's why I thought that.
It's invariant under what?
If you sum constants, you still have solutions.
Yeah, so the point is that there's no compatibility here. But that's why the price you pay is sort of funny asymptotics of the interface. So the interface sort of mediates between the incompatibility. It sort of explains the incompatibility between the two sides. And that's really the point of it. You pose data on the two sides, they have nothing to do with one another, and you have to get smoothly from one to the other somehow, and that's what that blow-up does. So that's the whole point. You don't need to respect compatibility. Yeah?
So if you had like a 90-degree angle and you had going on here and here and there, would you anticipate compatibility conditions then?
Yeah, absolutely. I mean, here's a classical thing which is explained by blow-up. Actually, I wrote this up in a little paper I wrote a couple of years ago. And it's something that, you teach to first-year PDE students, but it's not, it has some interesting ramifications. Sorry, this is a little diversion, but it's an interesting thing about why blow-ups are not a bad thing to do. So here's a fact that, again, if you've taught first-year PDE, suppose I have the heat equation in an interval cross R plus. Right, so I'm looking for a function u of t of x, which satisfies dt of u is equal to the Laplacian dx squared. Okay, fine. So suppose I specify it with, suppose I want the mixed Dirichlet-Cauchy problem. So I'm going to specify u at t equals 0 is equal to some 5x, and then u at t comma 0 is equal to, psi naught, and u at t comma 1 is equal to psi 1. Right, so this is one of the endless variations of stuff that you teach for separation of variables, right? Okay, so you do that, you can find a solution by expanding in Fourier series and blah, 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 right? And if you think about it, it's not smooth at the corners. It just isn't. Okay? However, if you blow up the corners, you have to blow up parabolically because there's a homogeneity involved here. So you sort of take it's called a parabolic blow up, but you blow up these corners like that, and it's smooth. Right? So now you think, well, big deal, you just made it smooth. That actually has some very nice consequences, and maybe I won't talk about them here, but you can ask about them. But so blowing up actually can take problems where you have no compatibility to things which are really smooth. So what's happening here is that this face here has, what are the typical compatibility conditions here? You need to know, that the derivatives of psi naught in this direction and the derivatives of phi in this direction sort of have matching conditions. If they don't match, then what happens here is you have a whole infinite hierarchy of ODEs for which those derivatives are kind of the boundary values. So I find a whole sequence of ODEs on this face here, which sort of intermediate between those non-matching derivatives. Okay. This actually is very interesting for semigroup theory. So that's what I wrote a paper on, that you can actually get a good semigroup. So if you take the heat semigroup on, let's say, classical Holder spaces here, it's not strongly continuous. And if you pass to this blow-up, it is strongly continuous. So, okay. So let me just say, what are a few problems that I'd still like to solve? Wow, there's a lot of them. But what was the problem that, well, first of all, what are some of the conclusions? I've told you in only very rough terms. But, for example, if we're solving, so in this sort of, in any case, here's something that's been known by many of these other brilliant people who've worked on these fractional Laplacians and bounded domains. So here's omega. If I have, Laplacian to the s of u is equal to 0 in omega, with, let's say, some sort of exterior condition, u restricted to omega complement is equal to some phi. So this is typically how you specify a boundary problem. You say what it is outside, you want it to be 0 inside. That's a special case of this. What can you say about the regularity of u at the boundary? And so, roughly speaking, u is going to look like, that's an x variable, u is going to look like x to the s plus I over 2. It's polyhomogeneity. So if phi is smooth, then u is polyhomogeneous, and there's this expansion of the interior. So that's a very well-known theorem, but that's derivable from this. If phi is only Holder continuous or something, you get sort of a corresponding regularity theorem for what this looks like. But the important thing here, and this is again what the numerical people were interested in, is it starts off with x to the s. Okay, so here's an open problem, which I don't think it's hard given all the stuff that I don't know the answer a priori. To tell you is suppose that omega is a square. Okay, so you can pose this, you know, there's a good weak theory of how you get solutions, or a good energy theory of how you get solutions. What's the regularity view of the boundary at the corners? So, well, hopefully by now you sort of see what you should do, which is to blow a bunch of stuff up. And you're going to have asymptotics that are going to depend on the directions of approach to the corners. And similarly, if you do this in higher dimensions, you'd like to know what's the corner and boundary regularity for if omega is a polyhedron or a piecewise. Okay, well, I think I'm going to stop a few minutes or less.
Are there any questions for Ray?
So these singularities that you have, like, usually you have like, can you have like higher order singularity?
How do you mean higher, like cusps?
Like, so you know that your solution has to blow up for some geometric reason, and you want to develop everything, but it's going to blow up in a...
Well, you expect, so like, for example, if omega looks like this, you're expecting some rate of blow up. Now, what I told you in the local problem was you have a rate of blow up which depends on the angle there. So, you know, what's going to happen here is you're going to have a spherical sector here. And there's going to be some spectral problem, some eigenvalue problem in the spherical specter, which is going to regulate sort of the order of blow up or decay as you go into that corner. So that's what they're doing.
Okay, so I imagine if you have like height, so you don't have a corner, which is a point, you don't have a line, like you don't blow up. If you have something higher, you come to like a blow up in higher dimension.
Oh, yeah, sure. So, absolutely. So here's something that I'm in the midst of writing up slowly. The local version of this, which is interesting. So this is joint work with Kerr Alvin and Jeremy Marzullo. So, you know, this is a theorem that, you know, could have been answered. Well, so, you know, if you study Dirichlet-Neumann numbers, suppose I have some domain in Rn. Right? So, you know, what's known about the Dirichlet-Neumann operator? If omega is a Lipschitz domain, then there's a Dirichlet-Neumann operator. You can get it by a list of abstract techniques. The problem with that, when omega is only Lipschitz, or the boundary is only Lipschitz, is that you know it as an operator. You don't, I mean, you know it as a functional analytic object rather than as a Schwarz kernel. Okay, so if you're trying to do sort of interesting things with Dirichlet-Neumann operators, like inverse problems or so on, you know almost nothing about them if omega is a Lipschitz domain. Okay, well, let's back off a bit and not look at fully Lipschitz domains, but let's look at the case where omega is a polyhedron, or slightly more generally, I can take the case where omega is a domain whose boundary is some sort of stratified space. So, you know, for example, it could have like an isolated conic singularity, or there could be sort of an edge in the boundary, or there could be some sort of, you know, complicated network of edges in the boundary, higher codimensions, so you can do things like that. So then the theorem that we're proving, let's take this case right here, right? So the point is that in this case, over here, the Dirichlet-Neumann operator is just a garden variety pseudodifferential operator of order 1, as I proved for you on Tuesday. Okay, what is it near here? Right? And the answer is it's a B pseudodifferential operator. So in this class of conic problems I talked about, it's not differential, but it's a first order B pseudodifferential operator. That gives you a very precise structure for what it looks like as an integral kernel near here. You know, if I have an edge in the boundary, then it's going to look like an edge pseudodifferential operator and so on. So again, this is this philosophy that it's very useful to know the precise structure of the Schwarz kernel, because then you can do things with it. You can understand mapping properties in different spaces. You can study inverse problems. You can look at asymptotic expansions. So, you know, the typical inverse problem for Dirichlet-Neumann is, you know, if you know the Dirichlet-Neumann operator, which is if you know the conductivity, you charge up the boundary and then you measure the conductivity. So this is the classical Calderon problem. If you understand the Dirichlet-Neumann operator, can you recover what was happening, what the domain looked like, right? So there's many versions of this problem. This is sort of, you know, one of the central problems of inverse problem theory. And so when there are corners or stuff, you know, one of the simplest things you can do is if you have a common point, can you recover how big that angle is, or what's the solid angle there? So,
You were question asked.
Okay, I'm just asking, in this approach, are there in that, say, for s equal to 1, you get a relative behavior of,
you get what?
you need to multiply by 1.
Yeah, so of course what's happening is that, and maybe let's sort of back up to the boundaryless case, okay? So I told you this theorem about pseudodifferential operators, they're normal and M cross M with, right? So, suppose I take an A, which is, suppose I take square root of Laplacian on M compact, right? So its Schwartz kernel is conormal with respect to the diagonal. What's happening as S goes to 1? Is that your question, right? Well, at S equals 1, you get a differential operator. And what's the Schwartz kernel of the differential operator? It's a delta function, or it's a derivative of delta functions on the diagonal. Okay, and 0 off the diagonal. So what's actually happening, and it turns out that if you transform it a certain way, it becomes a semi-classical problem. And so you actually get very sharp decay. So when S is 1 minus epsilon, you have something which is extremely small away from the diagonal. It's sort of peaked up near the diagonal, and all the off-diagonal stuff goes to 0 with very precise asymptotics. So you understand those things. I understand.
Are there any more questions? Okay, then let's thank Ray for providing a wonderful mini course.